How today's class is about how a project manager what a project manager can do to accelerate some of the activities in case he's already late. Like in most often, you'll realize that in project, things may not go on as planned. And therefore, these techniques will be very important for the project manager to adjust things and be able at least to push some activities more than even what was planned. And therefore, we shall look at two options of doing this. One of the ways is in an environment where resources are constrained, and another case is in an environment where resources are not constrained. When the resources are not constrained, we shall look at the avenues that are involved. Like for instance, when the resources are not constrained, it means therefore that the project manager can add additional resources to what we call some activities that were in a critical activities. In that case, hoping that the extra resource will reduce the timeline. If it was 6 days, perhaps we add 2 more people, then we expect now those activities will be done within a shorter period of time, owing the fact that that additional resource does not require any extra training or something like that. That is the assumption that we are making. And then we can add resources. Another case that we can do is we can sublet some project activities. For instance, we use what we call the consultants to do for us some activities. In that case, we are expecting that the consultant has more experience, and in that case, he is able to push those activities within a shorter period of time. Another option that we have is that of employing what we call dedicated project team. Having dedicated project team will ensure that at least now the activities are done slightly faster than when it is being done as planned initially. Then we also have different options where a project manager is working in a resource-constrained environment. When the resources are constrained, it means a project manager does not have any extra resources that he is able to implement, to add. In that case, therefore, the project manager can study what we call the network logic. Now, studying the network logic and rearranging the network logic such that the activities that were supposed to be done, what we call in sequentially, can now be done in parallel. So that means now we do what we call fast tracking. That technique by which you rearrange the network logic such that activities that were done after the other, what we call sequential activities, are now being done in what we call parallel, is what we are calling as fast tracking. So you can fast track. That is an option that is available for you, so that you can be able to reduce what we call the timelines on the critical path activities. Another thing that is available for you is now, the last resort is what we call as the scope, reducing the scope of the project. Now, reducing the scope, and if the stakeholders have agreed to it, you can reduce the scope of the project such that you can be able now to do less than what initially budgeted for. In that position, you will be in a position now to reduce what we call the timeline. Now, but for this unit, we want to emphasize more about what we call adding more resources, or what adding more resources is called project crashing. That is what we want to demonstrate with a typical example of a project scenario, then what a project manager needs to do when he's faced with a situation whereby he's doing what we call project crashing. So that's what we want to look at right now. We just want to look at, by this example, we have an example here of a project activities. We have activities A, B, C, D, E, F, G. These are the activities that will be provided in the project. Now, this is what we call how the activities are supposed to sequence one another, okay, the predecessor. And then now, this is the normal time. This is the normal time as budgeted. Initially, this is the normal time that you have been provided, and then this is what we call the crash time. How we want to reduce the timeline of what we call the project. We want to reduce activity A from 2 days to 1 day. We want to reduce activity B from 8 days to 5 days. We want to reduce activity C from 4 days to 3 days. We want to reduce activity D from 1 day to 1 day. It means now we don't need to do anything in activity D. It will remain unchanged. And then activity E, we need to reduce from 2 days to 1 day. And then activity F, we need to reduce from 5 days to 3 days. And then activity G, we need to reduce from 6 to 2 days. Now, this is what we call the normal time, and then this is the crash time. Likewise, every time, every activity has what we call cost element. Now, when you crash a project, definitely you increase cost. So you expect the crash cost slightly greater than what you call the normal cost. Okay? So we have all the normal cost for all the activities and also corresponding crash cost for all the activities. Now, the first thing that you are expected to do is find the minimum possible time of the project and the cost associated with it, given indirect cost per unit is $2,000 per day. Now, the procedure that you need to take when you have such a question is that, first of all, you need to draw the network so that we can be able to understand what we call the critical path. So that is what we start. And drawing the network, we only require the predecessor relationship and this activity and then the normal time, so that now we can be able to understand the critical path. So we begin crashing the project after we already understand the critical path, because the logic here is that we crash activities on the critical path because those are the activities that will assist us to reduce what we call the timeline that we are interested in accomplishing. So definitely we need now to do the network logic first, or what we call the network model. After that, we understand where do our critical path lie and how many paths do we have that we can be able to start crashing consequently, before we now come up with what we call the algorithm of crashing. So before that, we need now to first draw the network. So let's draw the network of this program. I'm still going to use what we call the activity on arrow. Okay. So I start off. So this is the first activity, activity A. Activity A begins. So activity A can begin. Activity B can also begin in the same manner. Activity B can also begin in the same manner. It means activity A and B are all running in parallel. So we can have what we call activity B here. Okay. So then activity C can start after A is complete. So we can begin activity C here after A is complete. And then activity D can start after B is complete. After B is complete, we can begin activity D. Okay. And then activity E can start also after B is complete. E can start after B is complete. So it means now we can have activity E here, activity E here. It can start after E is complete. And then we can have activity F, which needs to start after C and D is complete. After C and D is complete. So you look at this. In this situation, we are required to join activity C and D before we can generate what we call activity F. It means, therefore, that this activity D needs to join with this one first here, up here. So we say this is activity D. So that we can be able, CD, completing C and D, we can generate activity F. So that is now that condition that has brought that. And then activity G can start after E is complete. After E is complete here, then we can start perhaps assuming that activity G is somewhere here. Activity G is somewhere here. So now look at this. Activity F and G, we have not been told they are not joining. But remember, one of the rules of drawing the network is that we can never leave a network to join. It all flows from left to right, from what we call left to right continuously, and then we must have an end. It means, therefore, these two activities need to join together. So we can assume that their joining point is here, and we bring also F so that it can join here instead of hanging like that, because that is, we are committing a crime. We don't need to commit a crime in drawing network. And therefore, we need to ensure that we obey all the rules of drawing the network. So this is my model. So understanding this model is a prerequisite of doing correct crashing of the project. Okay. Now, next, once you've already drawn the model, the next thing that I need to do is I need to insert what we call the normal time for each and every activity. Activity A was given to be 2 days. Activity B was given to be 8. Activity C is given to be 4. Activity C is 4 days. Activity D is given to be 1. Activity 1 is 1 day. Activity the next one is E is 2 days, and then F is 5. F is 5. This is F, and then this is G. F is 5 days, and then G is given to be 6 days. So G is given to be 6 days. So now, using this, what you call the duration by which every activity has been provided, we can easily, this is 1 day, this is 4 days, this is 8 days. Now, using this, it's now very easy for me to know which is the critical path. So how many paths do I need to follow? So I can follow first the first path. I need to establish the paths. First path is A. I can follow A. I go to C, and then I come to F. So that takes me how long? That comes to 2 days plus 4 days plus 5 days. So this is 2 plus 4 plus 5. That gives me 11 days. So the first path only gives me 11 days. We need to go to the second path. Second path gives me how many days? We establish which is the longest path. So the second path can be B. we come to B, then I come to D, then I come to F. So this will give me B is 8 days, D is 1 day, F is 5 days. How long is that? This is 14 days. This is 14 days. Then for the third part that we need to follow is B. Then if I follow B, I come to E, then I go to G. I go to G. So when I follow this path, I will have B, which is 8 days, plus E, which is 2 days, plus G, which is 6 days. So this is like, this is 8 plus 8, this is 16. And definitely, this is where the critical path lies, because this is the longest. So the critical path we establish by examining the longest path. The first path, 11, 14, and 16. So 16 is the longest. So we come and mark it as our critical path like this. So we say this is the critical path, and therefore, all crashing of this project will be based on this critical path. So in that order, it means therefore that we need now to come to understand now the algorithm of doing what you call crashing the project. And one of the procedure that we need to establish is to identify what you call the crash cost per unit. Now, the crash cost per unit will be the basis by which we shall use to crash this activity. And remember, the objective here is to crash at a minimum cost as possible. Therefore, it means that when examining the critical activities, we shall identify the one which is least to, will make us to incur the least cost to crash. So we need to develop a column here which indicates what you call the crash cost per unit. So this is crash cost per unit. So this is simply the difference between crash cost and normal crash cost minus normal cost over what you call normal time minus crash time. So it's just the difference between these figures. So this is 15, this is 10. So 15 minus 10 is 5,000. 5,000, and the difference is time is 2 and 1. So this simply means the crash cost per unit here will be 5,000. What it means is that I will spend $5,000 to be able to crash activity A. Okay, so I need to know how much will I spend per day to crash activity B. So activity B is 6,000. 6,000, the difference in time is 8 minus is 3. So this 6,000 minus 3 is going to give me 2,000. So activity B, I will spend $2,000 to be able to crash activity B. I go to activity C. Activity C is 24 minus 20 is 14. 14, and the difference time is 1. So this simply means 14,000. I have to spend 14,000 to crash activity C. Now, this case, there is 0. Everything is the same. So I will not spend anything to crash. That activity is not supposed to be crashed. That is why you are finding the timeline is the same. So here is 15 minus this is 7,000. 7,000, and difference time is 2 and 1. So it means is 1. So this, I will spend 7,000 per day to be able to crash that activity. Okay. This, I will spend how much? This is 16,000 minus this is 10. Is 6,000. So 6,000 divided by 2 is 3,000 now here. Okay. Now this is 31 minus this is 18. 18,000. So this is like 18,000. The difference in cost, and then divided by the difference. So I suppose this is 16. So 16, it will remains 20, 25. So this, I suppose this is 16. So 16, it will remains 20, 25. So this, I will have to spend 4,500 to be able to crash the final activity, which is activity G. So I've already identified all the activities that I'm supposed to crash. But the most important thing is to identify which activities requires priority when I'm crashing. These activities are activity B, E, and G. So you come and circle activity B, activity E, and activity G. Why are these activities? Because these are the activities on the critical path. These are the activities on the critical path, and they're the ones that I need to crash. Okay, so I now consider which is the first activity I need to give priority. The first activity that I need to give priority, according to the crashing algorithm, is that the activity on the critical path that I will incur less to crash. So which one will I incur less to crash? What do I spend per day for B? B, I will spend what you call 2,000. Okay, E, I will spend 7,000. Okay, G, I will spend 4,500. So in the order of priority, I need to crash activity B first. So first crash, you come here and then write first crash. I need activity B. Activity B, I will crash for how many days? So let's look at that activity B. Okay, so this activity B, I have allowance of crashing activity B with 3 days. But look at what the first crash is. I want just to take 1 day. So when I take 1 day, I will spend 2,000. So I will spend 2,000. So that 2,000 for crashing that activity, it means that now the cost will move from, now what is the number of days of this critical path now will reduce from 16 to 15 days. If I do that, the critical path will move from 16 to 20 days. Now this comes now to, from 16, it comes to 15, but this second path also reduces because there is an element of P. So this one also will come to 13 days. This remains the same, this is 11 days, okay? So we go to the second crash. So the second crash, I can still move to activity, that same activity I can, because I can still crash it, activity B still, with another 1 day. So I spend an extra 2,000, so it moves the critical path for 14 days. This now moves to 14 days, this comes also to 12 days, okay? So I can also move the same to third crash. I still just crash what you call activity B, because I had allowance of crashing it from 8 to 5. So in with 1 day, I spend another 6,000. I will spend another 6,000. So when I spend another 6,000 here, I spend another 6,000. When I spend another 6,000, it will make now the critical path to comes to 13 days. This now moves from 14 to 13 days, and this comes to 11 days, okay? So this one and that are the same. This is now 13. So I've crashed this maximally. So activity B, I've crashed maximum up to now 5 days. So and I cannot crash activity B again. So I now consider the next activity, which is between E and G. Which one am I supposed to crash? So I look at E. I'm supposed to spend 7,000 to crash it. G, I can spend 4,000 to crash. So in order of priority, I will move to this. I will move to this G instead of E because it is cheaper to crash this, because the crash cost per unit is lower as opposed to crashing E. So I will come to G first. So when I come to G, I say the fourth crash is activity G. I crash 1 day. So 1 day I spend 4,500. 4,500. So that will reduce from 13 to 12 days. So I will reduce it from 13 to 12 days. Because activity G is almost in all this, my activity G is only in one line. So I can crash this activity D is only in one network. Remember, this is BEG. This is BDF. So this I can reduce this from to 12. So it is only this that will reduce to 12. And remember, this one was 11. So I can crash this G again, the fifth crash. I can crash this G again to 1 day, and I spend 4,500, and this will give me 11 days. As this becomes 11 days, and all this becomes the same, because this second part is 11 days, this is also 11 days. So I can say this is the maximum I can be able to go. It's the maximum I can be able to go because I was interested so much in the critical part. So I can reduce this. I can reduce this project from 16 days to 11 days. And now I need to know what is the corresponding cost. What is the corresponding? How much do I need to incur in order to crash this project? Now you add the total sum for this. You add the total sum for all this crashing. So you will add, you find 2,000 plus 2,000 plus 2,000 plus 4,500 plus 4,500. This is like 9,000 plus 6,000 is $15,000. So I will have to spend $15,000 so that I crash that project for 11 days. So now, what do I need to do? What now the total cost will I need to incur? Remember now, the cost of the project is given in terms of you add what you call the direct cost plus the indirect cost plus perhaps the penalty cost if the question gives you a penalty cost. And if we don't have, then you ignore. But in this case, we were given the indirect cost. So we will have to factor in indirect cost. And also now this is the direct cost. But remember, now you add the normal cost plus this extra, because this is only extra. So this is the extra amount that we need to spend. So we add the total normal amount. So the normal amount that we were given, you also need to get the sum of the normal cost. So this is 10,000 plus 15,000 plus 20,000 plus 7,000 plus 8,000 plus 10,000 plus 12,000. If I add this, I get this is 25. I get this is 25. So this is 27. 27. I get there to be 52. So that becomes, this is 52. So this is 8,000 plus, this is 18,000. I add 18,000, this becomes 70 plus 12, this becomes 82. So this is like $82,000. So this is the normal time. So normal cost. So we need to add this normal cost with the extra amount that we need to spend in crashing. And now this is $82,000 plus $15,000 will give me $97,000 as my direct cost. This is the direct cost. So after direct cost, you need to add what you call the indirect cost. Add indirect cost, and indirect cost is 2,000 per day. And how many days are we supposed to spend now in this project? When we crash it, it's 11 days. So 11 times 2,000, we shall get 22,000. Now, because we don't have penalty cost, therefore, we can only arrive at adding direct cost and indirect cost, which means 97,000 plus 22,000. So this becomes 9, this becomes 11. So 119,000. So this is now the amount that we need to spend. Associated costs associated with the crashing this project, $119,000.